Good evening. This week we're going to discuss the next concept in physics that we need to understand the motion of particles and bodies, which is that of kinetic energy. What is energy? Well, energy has a lot of different definitions that have been used over the years. The one most commonly found in textbooks is that energy is the ability to do work. Since we haven't yet defined what work is, this definition is a little unhelpful. What do we mean by work? Well, work is basically a force that's being applied to a body consistently over time in order to produce a certain change in its motion. We'll get to that a little bit later in this chapter. When we say that energy is the ability to do work, we mean that this energy could be stored up later to do work at some time in the future. That's what we'll refer to as potential energy, but we're sort of getting ahead of ourselves. That's going to be the topic of the following chapter. Energy can be defined in dictionaries as the level of activity or vigor of a body or particle. The basic concept being that particles that are traveling fast have more energy than particles that are traveling slowly. Dictionary definition is a little too imprecise to be used in highly mathematical fields such as physics, though it generally embodies the concept. The book defines energy in more formal mathematical terms. We can define it as a scalar quantity associated with the state of motion of a body or particle. We mean that it's a scalar, so it will depend on the velocity, but only on the magnitude thereof, since scalars don't have any direction associated with them. And as we said, particles that are traveling fast tend to have more energy than particles that are traveling slowly. How does this concept of mechanical energy relate to energy of other types that we may see in fields of physics? One common type of energy is heat energy. We know that a body that is very hot is radiating a lot of heat, and it tends to be more energetic than a particle that's slower. Well, what we define as hotness, what we feel is hotness or coldness of a body, has to do with the speed at which the constituent particles in the body are traveling. If the constituent molecules are traveling fast, then we have a hot body. If they're traveling slowly, we have a cold body. This is related to the concept of temperature. Temperature really has to do with the kinetic energy of a group of particles, often a gas or a liquid, although it could also be a solid. We're going to see this concept come up much later in this course. Why do we care about energy? What's so special about this quantity that we would spend 2 whole chapters in the book going over it? Well, it turns out that energy is conserved. By conserved, we mean that no matter what happens to a particle in its future movement through space, the total quantity of energy associated with it is always constant. This we refer to as the law of conservation of energy. This is also referred to as the first law of thermodynamics, and is usually stated as energy can be neither created nor destroyed. This is one of the fundamental laws of physics, and it's been found to always hold true. In Einstein's day, he was able to show that mass is a form of energy, and that the two can be transformed into one another. In this chapter, we'll be concerned with one of 2 types of mechanical energy that are covered in this course. That's kinetic energy, which is basically a measurement of how fast something is moving. Kinetic energy is defined as 1/2 the mass times this velocity squared. Velocity squared is a scalar quantity. Since we've already defined kinetic energy to be a scalar, notice that it's directly proportional to the mass. A more massive body moving at the same speed as a less massive body carries more kinetic energy. It takes more work, as we'll see shortly, to get such a body moving than it does a lighter body. The fact that it depends on v squared means that it increases rapidly with speed, not linearly, but by the square of the speed. Units of energy, there's many different units of energy that have been used. In the SI system, it's equal to mass times speed squared, which is kilograms meters squared per second squared. This is what we define as a joule. In the CGS system, the unit of energy is the erg. In other systems, energy may be defined as calories or other such units. For our purposes, we'll stick with joules. An example of how kinetic energy is related to the work of a body is an example of a body that's undergoing uniform acceleration. This illustrates what we mean by work. Suppose we apply a force F uniformly to a baseball. It has a certain mass, and by the equations of motion that we covered in a previous chapter, we know that the speed increases linearly with the time, and the distance, or the displacement of the baseball, to be more accurate, goes as the initial position x naught plus v0t plus 1/2 at squared. As the speed increases, the kinetic energy as we've defined it increases by 1/2 mv squared. Now, if we start out with having no initial kinetic energy, then the body's initially at rest. And so we can just say that, set v naught equal to 0, and we can say that v equals at. Squaring that, we have kinetic energy as 1/2 ma squared t squared. Since ma is equal to the force, we can remove it, and that just leaves us with the force times at squared. But notice that the displacement x of t minus x naught is equal to 1/2 at squared. Remember, we already said that the velocity, the initial velocity v0 is equal to 0. So if we substitute this into the equation, we have the kinetic energy K is simply equal to the force times the displacement. This is what we define as work. Force times the displacement through which the force acts on a body is the work that's performed on it by the force. So if a force is applied to a body over a certain duration, the kinetic energy increases by an amount equal to the force times the displacement. In other words, the kinetic energy increases by the work that's put into the system, or K final minus K initial equals the work. This is one statement of what we refer to as the law of conservation of energy. Now, this was for motion in one dimension, say along the x-axis. But we know that force is a vector, and it could be applied in an arbitrary direction. And it can in fact be applied in some direction other than the direction of motion, such as in uniform circular motion. In those cases, we define the work as the force dotted with the displacement, the scalar product of the force and the displacement. So if the force is applied at some angle theta to the direction of motion, that's equal to F times x times cosine of theta. Let's consider the very simple case of a body falling in a uniform gravitational field. We've already considered this kinematically, which is to say we derive the future time x of t of the body by integrating the expressions for equation of motion for a constant acceleration. Now we're going to treat the motion in terms of the total kinetic energy. The force, which is the weight, is just equal to mg. G is the acceleration due to gravity, 9.8 meters per second squared. Since the work is defined as the force times the displacement, work is equal to mgh, where h is the total distance fallen from the time the ball is released. Now, if the body starts initially at rest, we can set Ki, the initial kinetic energy, equal to 0, and therefore K final is just equal to 1/2 mv squared. Since by the law of conservation of energy this is set equal to the work, 1/2 mv squared equals mgh. the mass conveniently drops out. Therefore, we can rearrange and we can find the height equals v squared over 2g, or v, the speed, is equal to the square root of 2gh. In other words, the speed increases by the square root of the distance fallen. If we go back to Chapter 2, we'll see equation 216 on page 23 has a very similar form. If we replace a by minus g, and we set x naught equal to 0, so we define the origin to be the point at which the ball is released, and we set v naught equal to 0, we'll see these two expressions are equivalent. Speed goes as the square root of the distance fallen, or the distance fallen is directly proportional to v squared. This is an easier way to derive the same result, which shouldn't be surprising since the laws of physics have to be internally consistent. Let's look at a slightly more complicated problem. We have a ball that's thrown up in the air some speed v0. It's thrown up, it comes to rest midway through its path, and it returns back to the pitcher's mitt. And this question is, what is the speed at which it is traveling when it returns? Well, we know from the equations of motion that we had in Chapter 2 for one-dimensional motion under constant acceleration, y is v0t minus 1/2 gt squared. To find the speed as a function of time, we simply differentiate this with time, dy dt, and we get the familiar result v sub y equals v0 minus gt, which is a linear function of time. If we want to know what is the ball's state of motion at the time it reaches the catcher's mitt again, well, we define the starting height as y equals 0, so we simply set the y expression a quadratic equal to 0, and we can see that we could factor out a factor of t. One solution occurs at t equals 0. Obviously, the height is 0 at the time that we're starting, which is the way that we just set up the problem. The other expression is when the parenthetical is equal to 0, which is v0 minus 1/2 gt equals 0. Or, if we can rearrange, we have time equals 2v0 over g. This is the time at which the ball returns back to the pitcher's mitt after its initial release. If we substitute this into the second expression, the expression for vy, we get the result. Vy equals minus v0. The minus sign means it's traveling in the other direction. When it was first released, it was traveling up. Now it's traveling down, but it's traveling at the same speed. Well, what occurs on the left-hand side of this slide is analyzing the ball's motion in terms of kinematics. But let's look at the right where we can analyze it dynamically, which is in terms of work and energy. Initially, K initial is 1/2 mv0 squared, where v0 is the speed at which we originally throw the ball up. While it is climbing, gravity is constantly performing work on the ball. Note that the work is negative because the force due to gravity is downward, whereas the ball's motion is upward, so the dot product between the two results in a negative number. Gravity is performing work to decrease the kinetic energy, or negative work is being put in the system to cause it to slow down. The ball will stop moving at some point, and that occurs when all the kinetic energy is removed. So this occurs at some height h such that kf minus ki is 1/2 mv0 squared minus 0, or the difference is equal to the initial kinetic energy, and that we set equal to mgh. If we rearrange, we solve for h, we find h equals v0 squared over 2g. So that's an expression that we found by using dynamics for the maximum height at which the ball reaches. The ball must then fall through the same height h. Now the same work is put into the system except that it's positive. mgh is equal to 1/2 mv squared, or solving for v, we have the familiar result v is the square root of 2gh. If we substitute the expression for h into this, you can do the math, but find that v simply equals v0. Now we've actually lost a minus sign because when we square a value, we lose any information about whether it's positive or negative. So taking the square root, we should actually say that v equals plus or minus v0. The plus value would occur at the time t equals 0 when the ball is first thrown up. The minus will occur when it returns. Now consider how kinetic energy applies to projectiles. Let's move away from the simple idea of throwing a ball straight up and consider a projectile that might be launched at some angle. By conservation of energy, we've proven the ball will return at the same speed. On the way up, negative work is done to reduce the kinetic energy or reduce the speed of the particle. On the way down, positive work is done by gravity to increase the kinetic energy and the speed. It will turn out that the change in kinetic energy between 2 points equals the net work between the 2 points, which in a gravitational field, where the force always points straight down, is simply equal to mg times the difference in the two heights. This applies whether the particle is launched straight upward or it's launched out horizontally, or at some intermediate angle. We can use this expression to find its speed at any point along its path. We simply determine kf, the final kinetic energy at some time that we're interested in, set the speed there equal to some value, here we've called it v1. Then we subtract the initial kinetic energy, and we set that equal to the net work, which is just minus mg times the difference in heights. We have to be careful that we keep track of our signs correctly. We always have to ensure that when positive work is put into the system, it results in an increase in kinetic energy. When negative work is put into the system, it results in a decrease in kinetic energy. Alright, let's try a slightly more complicated problem. Consider the example of, again, a ball thrown straight up at some constant speed. Now let's ask ourselves, what is the speed when it returns halfway back to the pitcher's mitt? It's a little bit more complicated, but we can still use dynamics to solve this particular problem. We'll define half the height equals to 1/2 h, where h is the maximum height of the ball. And we want to know what is its speed at this value. Well, we'll set up our expression kf minus ki, where the final speed we'll define as v1 and the initial speed as v0. That's equal to 1/2 mv1 squared minus 1/2 mv0 squared. We can take out the common factor of a half m, and so we see it's proportional to v1 squared minus v0 squared. Let's then set this equal to the work, or the net work between the 2 points. Since it's related to only the difference in height, that's equal to minus mg times h. Now, we've seen that the total height is related to the initial speed by h equals v0 squared over 2g. Since h prime is halfway up to the maximum height, that's equal to v0 squared over 4g. So let's substitute into this expression. The g cancels out, and so we're left on the right hand side of the equation with minus 1/4 mv0 squared. That gives the expression on the second line. In order to solve this, let's eliminate the extraneous quantities of a half m. Let's get rid of that. Then we're just left with v1 squared minus v0 squared equals minus a half v0 squared. This is easy to rearrange and solve for v1, and we see the interesting result that v1 is equal to v0 over the square root of 2. To summarize, using the dynamic equation of conservation of energy, kF minus ki equals the net work done, we found that when a ball is thrown straight up and it returns down to half of the maximum height achieved, its speed is equal to the initial speed divided by the square root of 2. Now consider a projectile that's launched outward at some angle. It could be launched outward at 90 degrees, so it's launched horizontally, or it could be launched upward or downward at some other angle. Either way, it's going to follow a parabolic trajectory. What is the change in kinetic energy? Well, we haven't proven it yet. We'll do that at the end of this lecture. But the change in kinetic energy is still equal to the net work performed. This law of conservation of energy is universal, and it does not apply to only cases of uniform acceleration or motion in one dimension. It turns out that the change in kinetic energy is still equal to the mass times the acceleration of gravity times the height difference between the 2 points. This is irrespective of the pathway shown. Now the initial kinetic energy is still going to be equal to 1/2 mv squared. And since it's a scalar, it doesn't care what direction the velocity is originally pointing in. It only cares about the magnitude. And the increase is still going to be equal to mgh. This is the idea of path independence. The gravitational field is what we call a conservative field, where the work performed only depends on the coordinates of the 2 points, the starting point and the finish point. No matter what kind of complicated path a baseball may follow when traveling from one point to another, the change in kinetic energy is always equal to mg times the height difference between the 2 points. This is something that we'll see is very important when we treat potential energy in the following chapter. Now let's consider our next sample problem. In this case, it's a body in uniform circular motion. We know that a body under uniform circular motion undergoes a centripetal force, mv squared over r. Now in this case, the velocity of the body changes, but it only changes direction. It has constant speed as it continues to revolve around the center of curvature. So, by our definition of kinetic energy, the kinetic energy is equal to constant. If we consider that at some infinitesimal time dt, the body has moved some distance, x minus x naught, which is equal to the velocity times dt. Therefore, the change in position, x minus x naught, at every point in time is pointing in the same direction as v. That's the direction of motion. But the direction of motion is at right angles to the force. So by our definition of work, no work is performed. No work is performed because the speed does not change. If the speed does not change, the kinetic energy does not change. Therefore, in such cases where the force is at right angles to the direction of motion, no work is performed. Alright, let's think about another case. Let's think about the force that's applied to a wall. If we push on a wall, we can exert a force on the wall, and by Newton's third law of motion, the wall exerts a force back on us. Our force results in the equal and opposite reaction force. The wall doesn't move. It's stationary, unless we push very hard. Have we done work? Well, we may get very tired. We may exert ourselves if we do this for a long time. That's the colloquial concept of work. The technical concept in the field of physics is a little bit different. We would say we do no work on the wall because there is no net displacement. Notice that it's a net work. It's not simply the force, but the net force, which includes the reaction force of the wall back on us. It results in no displacement, and therefore there is no work done. So it takes no work to push on a wall. It takes no work to hold a piano, although I venture that if you were to do this all day long, you'd get very tired. It does do work to walk 10 miles, even over flat ground. For although we may not be working against gravity in the sense of changing our elevation, we still have to put in energy because there are frictional forces that result in dissipation. If we stop walking, we'll very quickly come to rest because of the frictional forces acting on our body. This would be somewhat different if we were, say, skating on a lake, where we could coast long distances without putting any additional work in. Now consider the idea of a ball that rolls against a wall. We say rolling across a flat floor, so we can basically neglect any change in elevation that occurs. When the ball hits the wall, it does no work on the wall, and by conservation of energy, it must rebound with the same kinetic energy, since change in kinetic energy is equal to the work. So, when a ball hits a wall and rolls back, it rebounds at exactly the same speed as before. This is what we coincidentally call an elastic collision. This wouldn't be the case if the ball were to hit another ball, either a very massive ball or one the same mass or a lighter ball. We'll see how to treat such things when we talk about the chapter on momentum. But for now, just consider that if a ball hits an object that is much more massive than itself, but not considered infinitely massive, both objects will recoil, and therefore there will be work done by the force, and so the kinetic energy of the ball after the rebound will be less than the initial energy. A wall can be essentially treated as an infinitely massive object. Now let's talk a little bit about springs. We already talked about strings. It's important not to confuse the two. A string is an object that basically transmits a force, which we call the tension, uniformly along its length. A spring, on the other hand, is an object that can either compress or elongate, and as a result of that, it exerts a force. Before we talk about springs, let's just back up a little bit and consider forces and work from the perspective of vectors. We define work as the force, the scalar product of the force and the displacement, where the force is constantly applied over the distance traveled. We just get this expression, W equals F dot X. If the force is variable, however, we have to do what we always have to do when we're multiplying two quantities, one of which, or both of which, are changing. The product becomes an integral. An integral is nothing more than the product of two quantities, one or both of which are changing. So we define work as the integral of f dot dx. Each infinitesimal element of work, dw, is equal to the force dotted with dx, where dx is the displacement element, which is a tangential vector to the direction of motion, as shown here in this diagram. We integrate from the original position 0 up to some maximum position x. So this integral results in the total work, which, as we said, is the change in kinetic energy. Now force, being a vector, we can resolve into components. We can resolve into x and y components, or, what's more convenient here, we can resolve it into normal and tangential components. The normal component is at right angles to the direction of motion. Since it's at right angles to the direction of motion, Fn dot dx is 0. Therefore, the normal force, an example of which was the centripetal force we encountered in uniform circular motion, does no work. Only the tangential force can do work, because only the tangential force has a component in the direction of motion and can result in a non-zero work dw. This is a general relation that we'll find is always true. Okay, let's talk about the force on a spring. First we'll talk about a spring in one dimension. We don't need all that vector stuff from the last slide, but we do need the concept of work as an integral. We can derive to a very good approximation the force of reaction exerted by a spring when it is compressed to distance x is equal to minus kx. What do we mean by this? When x, the net displacement of the spring, is 0, we'll define that as the equilibrium position. That's for a spring that has just happened to be sitting on a table, not experiencing any particular force and having its natural length. We'll fix one end of the spring and we'll define the position of the other end as equal to x. And we'll define x equal to 0 for an unstretched spring. So when x is negative, in this example above, then we've moved one end of the spring to the left, which means it's been elongated. When x is positive, we've moved it to the right, which means it's been compressed. The net force that we have to exert in order to do this is F, and it's proportional to the distance that we either elongate or compress it. This is what's commonly referred to as Hooke's law, but it's not really a law, not in the same sense as conservation of energy. It's more of an experimental approximation to the behavior of real springs. If we take a spring like a slinky and we stretch it far enough, eventually it will no longer return to its original shape, and it will no longer resist any further attempt we have to stretch it. So a real spring will eventually be stretched past what we refer to as its elastic limit, which is the range over which this Hooke's so-called law applies. So a real spring really, if we stretch it far enough, exhibits the behavior on the right. Alright, let's consider a spring in its equilibrium position. The force is equal to 0. If we compress the spring resists our compression and it wants to push back, so it exerts a reaction force equal to the applied force. If we compress it in one direction, the force will be to oppose it, and that's why the force law has the negative sign attached to it. Similarly, if we elongate it, it wants to contract. Again, the force is opposite to the direction in which the deformation occurred. Now, how do we apply the work to this? Well, we have to set up an integral. It's the integral of f dx from the initial position to whatever the final position is. Again, this is relative to 0 being at the equilibrium. If we integrate this expression, we get a result that's quadratic in x, or work is minus 1/2 k times xf squared minus xi squared. Let's look at a sample problem. How we would apply this to determining the speed at which an object attached to a spring is traveling after being compressed a certain amount. Consider a mass m is compressed against a spring through a distance x, which is then released. At the point at which it passes the equilibrium position, the spring will slow down and eventually it will start to contract in the other direction. Assume that the mass is not attached rigidly, but is just pushed against a plunger so that at that point the mass can become detached. We want to know what is the speed at which it is ejected. Well, the work done in compressing the spring through a distance x is minus 1/2 kx squared. This has to be equal to the change in kinetic energy. Since the kinetic energy is initially 0, the final kinetic energy minus initial is just 1/2 mv squared. And we set that equal to 1/2 kx squared. Again, we have to be careful of signs. When we initially compress the spring, what we're doing is we're storing energy in the spring for future use. When we release it, the spring exerts a force to the right in the case of the diagram above, and it exerts a force in the direction of motion, so it does positive work on the body. This results in an increase in kinetic energy. So the correct sign is as shown. 1/2 kx squared equals 1/2 mv squared. We rearrange, then we have an expression where the final speed is proportional to the distance at which the spring was compressed. The constant of proportionality is related to the k, the spring constant, and the mass. A similar problem is found on page 151 of the book. In this case, we have a body that's sliding into a frictionless spring at some speed v, and we want to know what is the maximum distance the spring is compressed. Well, the work is equal to the change of kinetic energy, or the change of kinetic energy is equal to the work. So therefore, this is really the opposite of the other problem. We set K final equals 0 because at the point of maximum compression, the body is brought to rest. And so K initial is 1/2 mv squared, and this is also just the change in kinetic energy. We can set up our work relation for the spring, and we have the end result of minus 1/2 K times xf squared, where xf is the final position, the maximum compression of the spring. And that equals minus 1/2 mv initial squared. Solving, we have the same relation. The xf, the final compression distance, is proportional to the initial speed. Although in this case, instead of the square root of k over m, we have the square root of m over k. It's a little bit different, but essentially the same physics applies. Either way, we have the same interplay between the work, the kinetic energy, and the forces involved. Now let's consider a more complicated problem. Let's consider a mass that's connected to two springs, one of which has spring constant K1 and one which has spring constant K2. We'll attach them to the mass, and we'll be kind enough to attach them when neither spring is compressed. And therefore the equilibrium position of the whole system is still going to be defined at x equals 0. Now consider what happens when the spring is compressed. First we compress to the left. When we compress to the left, the spring on the left experiences a reaction force minus K1x. Since we've compressed to the left, x is now negative. The force is positive, meaning the force points to the right. Again, we have a minus sign. But spring 2 is stretched, so it also experiences a force, in this case equal to minus K2x. Again, the force is to the right. The force of the left-hand spring is to the right because we're compressing the left-hand spring. The force due to the right-hand spring is also to the right because we're elongating the right-hand spring. We still get a negative sign in the force expression because the positive x for the left-hand spring is the same as the negative x for the right-hand spring because they're attached in opposite directions. Now we said the change in kinetic energy is equal to the net work. The net work is related to the net force, which in general is a vector. In this case, since we're still talking about motion just in one axis along the x-axis, we simply add them. So we have the net force is equal to F1 plus F2, which is equal to minus K1x minus K2x. Or the net force is equal to minus x times a new spring constant, which is equal to K1 plus K2. We can treat this as the spring constant of an equivalent spring. Now we simply plug this into the work equation. And we get the end result from integrating that the work is equal to minus 1/2 x squared times the new spring constant k, where k is K1 plus K2. Thus we see the same relation holds even if we have complicated systems of more than one spring. Does this also hold when we go from one-dimensional to two- or three-dimensional motion? let's consider a three-dimensional spring. This is a little difficult to draw, so it takes a little bit of setup. Imagine that we have a hollow cube, and we attach a spring to the center of each face of the cube, and we attach a mass which sits right in the middle of the cube. Now we can deform the springs in any direction we want, so the particle that's attached to the springs can move in any number of complicated patterns. We may think of it as undergoing some kind of complicated orbit within the cube. Let's also consider that the spring constant of each of the 6 springs it's attached to is the same. We'll just call it K. We're also going to assume that the connection point to each of the faces is variable, that the spring can actually move. Why do we do this? We do this to decouple the system. In other words, if we compress the springs, one of the springs in the x direction, doing so would have the effect of elongating the spring in the y direction normally. This makes the equation of motion much more complicated. If we could assume the connection points are free to move, then we're making the assumption that compressing in the x direction does not affect either the y or the z coordinates, so they can all be treated as independent. This is a bit of a contrived example, but it illustrates some of the physical principles nicely. Since we're in 3 dimensions, we have to use the vector form of the work equation, W equals F dot x. But we know that the force we can compose into components Fx, Fy, and Fz. Similarly, dx as a differential vector is simply a vector made up of the differentials in the different coordinates, dx, dy, and dz. We take the dot product and set up the integral. We get f dot dx is fx dx plus fy dy plus fz dz. This is a nicely decoupled expression because we have one term that only depends on x, one that only depends on y, and one that only depends on z. But the sum of an integral can be split into terms, so we really have 3 integrals. For instance, the integral of the work in the x direction, is the integral of fx dx from x0 to some future displacement x1. Notice we have 2 springs in the x direction, 2 in the y, and so on, but we can simply use the same expression with the equivalent value k, as we've shown in the previous example for a one-dimensional mass attached to 2 springs. So the work, we have 3 relations. We have the work due to the displacement in x, the work due to the displacement in y, and the work due to the displacement in z. And they're all equal, which is basically because we set up the same spring constant in each case. Now, let's do a little sample problem. The force is equal to minus kx, since we've defined the spring constant of each spring to be equal to k, and we have 2 in the x direction. That means that the force in the x direction is minus 2kx. Since all the springs are the same, the total vector force is just equal to minus 2kx in the x direction, minus 2ky in the y direction, and minus 2kz in the z direction. Plug this in and we get the very simple expression work equals minus kx squared minus ky squared minus kz squared. Notice the 1/2 went away. That's simply because we have 2 springs working in each direction. So we can see the total work is a sum of terms. Each term only accounts for displacement in one of the 3 directions. We also know that the work equals the change in kinetic energy, 1/2 mv squared. So we have the final expression, 1/2 mv squared equals kx squared plus ky squared plus kz squared, which we can also write as kr squared, where r is the distance from the center of the cube. This is a very nice and simple expression. It's the three-dimensional analog of the one-dimensional expression we had earlier. And let's think about the physics for a minute. If we think about setting up a mass in the middle of this cube that's attached to the 6 springs, and then we move it to some arbitrary point within the cube and we release it, it's going to exhibit some oscillatory motion back and forth, and in general it could follow some complicated pathway within the cube. But no matter where we are, we can instantly tell you what the speed is simply from this equation, 1/2 mv squared equals kr squared. No matter what complicated path it follows, it's very easy to predict what its speed is at any point in time. Of course, if we know the speed, we also know the velocity, because we can define the tangent vector to the direction of motion. This is how a very complicated problem can have a very simple solution just from applying first principles. This problem would probably be much harder to solve if we were to try to solve it using kinematic equations, but by using the concepts of work and kinetic energy, we have been able to vastly simplify the problem. Now, we've kind of taken for granted that this work-energy relation applies when we have a non-constant force. We derived it for a constant force, and then we simply took the integral, we assumed that everything worked out and all the equations still held. The proof of this is actually the case, occurs on page 153 of the book. Now let's confine ourselves to one dimension, because we've already shown that because we can split a vector up into components, and we can treat each component separately, that if we have a result that applies for one dimension, we can apply it to a 2- or 3-dimensional system just as easily. What we have here, though, is we have to show that this relation is true even if we have a variable force. Define the force as the integral of f of x dx. Using Newton's second law, the force is simply equal to ma. So it's the integral of ma times dx. We then substitute dv dt for the acceleration. That's the definition of acceleration. We then have dv dt times dx. In order to resolve this to the point where we can solve it, we'll employ the chain rule, where we simply have an expression dv dx times dx dt is equal to dv dt. That's simply the chain rule, and we can see that it is equal to dv dt because the dx's cancel and we rearrange, we get the same expression. But dx dt is equal to the speed. So let's substitute. Let's substitute v directly for that. Then we get dv dx times v times dx. Well, because the dx's can now be canceled, this is just equal to v dv. So after a bunch of complicated algebra, we have the end result. The work is equal to the mass times the integral of v dv. That becomes a simple integral, which has a solution 1/2 mv squared, evaluated between the limits of integration vi and vf. The end result is the work equals 1/2 mv final squared minus 1/2 mv initial squared. But we recognize those two terms as being the definition of the final and initial kinetic energy. Therefore, we see that even if we have a variable force, the work equals the change in kinetic energy. Okay, there's also the concept of power. Everyone's familiar with electric power. It's measured in units of watts. Watts are energy divided by time, so 1 watt is equal to 1 joule per second. In terms of basic SI units, it's 1 kilogram meter squared per second cubed. Everyone's familiar with this idea of a light bulb. You have 75 watt light bulbs, 100 watt light bulbs, and so forth. In that case, we're talking about heat energy. So it's the amount of heat radiated, or light, radiated per unit time. Remember, the heat energy is related to the kinetic energy of individual molecules. In this course, however, at least for now, we're talking about power in terms of mechanical energy, and it's the change in kinetic energy per unit time, or work per unit time. The average power is defined as the total work divided by the total time interval that work is applied. The instantaneous power is the derivative of work with time, dW dt. We already have an expression for work. Let's see if we can derive an expression for power. If work in 3 dimensions is F dot x, then power, which is defined as dW dt, is the derivative of F dot x. This may be a form of the derivative product rule that you're unfamiliar with. Remember, the derivative product rule says that if you have a product of 2 quantities, say u and v, then the derivative is the derivative of the first, du dt, times v. And the derivative of the second, dv dt, times u. And they're added together. Well, this also applies to vector quantities. When we have 2 vectors that we take the scalar product, it's the scalar product of the first with the derivative of the second plus the second scalar product with the derivative of the first. In this case, we have df dt dot x is the first term. But for now, we're confining ourselves to cases in which the force is constant. So we're defining df dt equals to 0. So the first term drops out, and we are left with only the second term, f dot dx dt. But dx dt is the speed. So we see in cases where we have a constant force that's being applied, the power is equal to the force dot product with the velocity. Again, since the velocity is in the direction of motion, if the force is at right angles, as occurred in centripetal motion, then the power was equal to 0. Well, this is a basic result. Now we've considered kinetic energy, work, and power, the basic building tools of dynamics. We've also seen a little bit about energy that's stored in a system, such as a spring, or represented by the height difference between 2 elevations, which we can think about as energy is being stored in the gravitational field. Either way, this concept of energy being stored leads us directly into the idea of potential energy, which is energy that's stored for later use, for later transformation into kinetic energy, for example. We'll see this more fully in the next chapter, because it's the total energy, the sum of the kinetic and the potential, which is the conserved quantity.